Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a paper that really struck a chord with me. We can't understand AI using our existing vocabulary. It suggests that our current ways of thinking and talking about AI might be fundamentally limiting our ability to truly understand it and move forward.
Yeah, I saw that one too. It's a bit of a provocative title, isn't it? Almost saying we're all just fumbling in the dark here, even with all the progress we've made in deep learning.
Provocative, yes, but I think it's also spot on. We're using language and concepts rooted in how we understand intelligence to describe something that may be operating on completely different principles. It's like trying to describe quantum physics with Newtonian mechanics. It just doesn't fit.
Exactly. And I think that's especially true when we talk about things like understanding or reasoning in the context of AI. We're projecting our own cognitive processes onto these systems, and that might be blinding us to what's actually going on under the hood.
That's a great point. Like when we say an AI understands a sentence, what does that really mean? Is it just recognizing patterns and spitting out a statistically likely response? Or is there something more fundamental happening?
Well, I think with the scale we're seeing in models like GPT-4, it's getting harder to dismiss it as just pattern recognition. The ability to generate novel text, translate languages, even write code, it's starting to feel like something more akin to understanding, even if we can't fully articulate what that understanding is.
But isn't that just a really sophisticated form of mimicry? It can generate text that looks like understanding, but does it actually have a coherent model of the world? Does it understand cause and effect, or can it just predict the next word in a sequence?
And that's where I think spatiotemporal reasoning comes in. These models are largely atemporal and aspatial. They don't really understand the relationships between objects in space or the flow of events over time. They're just crunching data in a high-dimensional vector space.
Yes, and I think that ties directly into this vocabulary issue. We don't have the language to describe how these models are actually representing information, because it's so different from how our brains do it. We are not able to describe what we know, so how can we translate that into design?
Okay, but even if our vocabulary is limited, isn't the progress we're seeing undeniable? I mean, look at AlphaFold solving protein folding, something that seemed impossible just a few years ago. That's got to count for something, right? Even if we don't fully grok it, it's working.
AlphaFold is impressive, no doubt, but it's still a specialized system. It's not like it can suddenly solve other problems outside of protein folding. It's highly optimized for a specific task, which is, again, different from general intelligence.
And even with AlphaFold, we're still struggling to understand why it's making the predictions it is. It's a black box. We can see the input and the output, but the intermediate steps are largely opaque. We're still not able to reason about the system's reasoning.
Exactly. We can't open it up and say, aha, it's using this particular physical principle to predict the structure. It's just a complex network of weights and biases. We can't readily translate its internal representation into something we, as humans, can understand. It's like we are facing a vocabulary gap in reverse. We can understand it, but how do we replicate it?
So are we saying that we're stuck? That we've hit a wall in AI research because we can't even describe the problem properly?
Not stuck necessarily, but maybe we need to take a step back and reevaluate our approach. Instead of just scaling up deep learning models, maybe we need to explore alternative architectures that are more amenable to human understanding and allow for more explicit reasoning.
I agree. I think we need to look at how the brain actually solves problems, especially when it comes to spatiotemporal reasoning. How does it integrate sensory information, create internal models of the world, and plan actions over time? I suspect the core algorithm needs to be able to translate between different coordinate representations, something current deep learning struggles with.
And that's where I see the potential for neuroscience to really inform AI. If we can understand the underlying neural processes that give rise to intelligence, we can start to design algorithms that are more biologically plausible and, hopefully, more interpretable. Perhaps looking into neuromorphic computing would be of assistance here.
But isn't that a bit of a romantic notion? I mean, the brain is incredibly complex. We don't even understand how consciousness arises, let alone how to replicate it in a machine. Are we really going to reverse engineer the brain to build AGI?
It's not about perfectly replicating the brain, it's about taking inspiration from it, looking at how the brain represents and manipulates information, how it integrates symbolic and subsymbolic processing, how it learns and adapts. These are all valuable clues for building more intelligent systems.
Yes, it's about extracting the principles that the brain uses, not necessarily copying the implementation detail for detail. What I am saying is that we shouldn't dismiss the wealth of solutions evolution has uncovered in biology in favor of mathematical elegance.
Exactly. Think about the visual cortex, for example. It's not just a bunch of layers of neurons. It's a highly structured system that performs specific computations at each stage. We can learn a lot about how to build robust and efficient vision systems by studying the visual cortex.
Okay, I see your point. But even if we do take inspiration from the brain, how do we bridge the gap between the biological and the artificial? How do we translate these neural principles into algorithms that can run on silicon?
That's the challenge, of course. But there are already promising approaches, like spiking neural networks and neuro-symbolic AI, that are trying to do just that. They're not perfect, but they're a step in the right direction.
And I think we also need to develop new programming paradigms that are better suited for expressing spatiotemporal relationships. Current programming languages are largely based on sequential execution of instructions, which doesn't really capture the parallel and distributed nature of brain processing.
It's like we're trying to build a cathedral with Lego bricks. We need new building blocks and new architectural principles. That is the role of biologically inspired architectures.
So, what are some concrete examples of how this vocabulary problem is holding us back in specific AI applications?
Take natural language processing, for example. We have these massive language models that can generate fluent text, but they often lack common sense and can make bizarre or nonsensical statements. That's because they don't actually understand the meaning of the words they're using.
Yes, I have seen this. I am pretty sure it is because the understanding of semantics is not complete, due to the models being unable to translate text to other representational spaces. It's like they're just manipulating symbols without any real grounding in the world.
Exactly. They lack what we call embodied cognition. They don't have a physical body to interact with the world, so they can't learn the meaning of words through experience. They're just learning statistical correlations between words.
Okay, but what about image recognition? AI can now identify objects and images with superhuman accuracy. Surely that's a sign of genuine understanding, right?
Again, it's more about pattern recognition than true understanding. An AI can identify a picture of a cat, but it doesn't understand what a cat is. It doesn't know that cats are animals, that they have fur, that they meow, that they chase mice. It just sees a collection of pixels that match a certain pattern.
And it's easily fooled by adversarial examples, images that are slightly modified to trick the AI into misclassifying them. That shows that the AI isn't really seeing the cat, it's just seeing a specific pattern of pixels that it has learned to associate with the label cat.
Right. The AI's internal representation of a cat is very different from our own. It's not a rich, multifaceted concept. It's just a point in a high-dimensional feature space. This limits its ability to generalize to new situations or to reason about cats in a meaningful way.
So, if our current vocabulary and frameworks are inadequate, what should we be focusing on instead? What are the key areas of research that could help us break through this barrier?
I think we need to develop new AI architectures that are more amenable to symbolic reasoning. Systems that can explicitly represent knowledge and manipulate it using logical rules. Neuro-symbolic AI is one promising direction.
I think we need to focus on spatiotemporal reasoning, developing algorithms that can understand the relationships between objects in space and the flow of events over time. This requires new programming paradigms and new ways of representing information.
I think we need to draw more inspiration from neuroscience. Studying how the brain represents and processes information can give us valuable clues for building more intelligent systems. We should pay particular attention to neuroplasticity and dynamic systems.
Okay, so neuro-symbolic AI, spatiotemporal reasoning, and neuroscience-inspired architectures. That sounds like a pretty ambitious research agenda. Where do we even start?
I think we can start by focusing on specific tasks that require both symbolic reasoning and perceptual abilities. Things like visual question answering or common sense reasoning. These tasks force us to integrate different modalities of information and to reason about the world in a more human-like way.
I think we can start by developing new benchmarks that specifically test spatiotemporal reasoning abilities. Current benchmarks are often too focused on pattern recognition and don't really capture the complexity of real-world reasoning. We need tasks that require AI to understand the physical properties of objects, their relationships to each other, and how they change over time.
And I think we can start by building more realistic models of the brain. Models that capture the intricate interplay of electrical and chemical signals, the role of glial cells, and the emergent properties of neural circuits. These models can then be used to test different hypotheses about how the brain works and to inspire new AI algorithms.
So, it's a multidisciplinary effort. We need computer scientists, neuroscientists, psychologists, and even philosophers to work together to tackle this problem.
Absolutely. This isn't just a technical problem. It's a fundamental question about the nature of intelligence. We need to understand what intelligence is before we can hope to replicate it in a machine.
And we need to be open to the possibility that our current understanding of intelligence is incomplete or even wrong. We may need to develop new ways of thinking about intelligence that are less anthropocentric and more focused on the underlying computational principles.
Yes, and that gets back to the original point of the paper, that our current vocabulary is limiting us. We need to find new ways to describe and understand AI, new metaphors, new frameworks, new ways of thinking about intelligence itself. It feels like we are on the cusp of an important breakthrough.
All right, I'm convinced. It's time to throw out the old dictionary and start writing a new one for AI. Maybe then we can finally understand what these machines are really doing and unlock their full potential.
I am keen on this idea. It is true, however. I think we need to move past just refining what we think intelligence is and start to redefine it entirely. If the basis on which we think about intelligence itself is flawed, then it doesn't matter what we change. The changes will all exist on the same flawed foundation.
Yes, and maybe also question what we think the role of AI is in society. Perhaps if we can focus on that aspect, we may uncover answers to the problems we are trying to solve.
These are all fantastic points. Let's turn to the future. Where do each of you see the most promising avenues for future research, building directly from this discussion about our vocabulary limitations?
From my perspective, I think the development of more robust neuro-symbolic systems is crucial. We need to find ways to seamlessly integrate symbolic reasoning with the perceptual abilities of neural networks. Future research should focus on developing new architectures and training methods that allow for the efficient and effective combination of these two approaches. Specifically, I'd like to see more work on systems that can learn symbolic representations from raw sensory data and use those representations to reason about the world.
I'm most excited about research into spatiotemporal reasoning. I think we need to move beyond static representations and develop algorithms that can understand how objects and events change over time. Future research should focus on developing new programming languages and data structures that are better suited for representing spatiotemporal relationships. I'd also like to see more work on developing new benchmarks that specifically test spatiotemporal reasoning abilities. Benchmarks that require AI to understand the physical properties of objects, their relationships to each other, and how they change over time. I think an ability to translate from our visual perceptive coordinate system to some other representation would be a great leap forward.
From a neuroscience perspective, I see tremendous potential in exploring the role of neuroplasticity and dynamic systems in AI. The brain is constantly adapting its structure and function in response to experience, and I think we can learn a lot from this. Future research should focus on developing AI systems that can learn and adapt in a more flexible and robust way. This could involve incorporating principles of synaptic plasticity, neuromodulation, and neural oscillations into AI architectures. I'm particularly interested in how we can use these principles to build AI systems that can learn from small amounts of data and generalize to new situations.
Well, I still think that scaling up deep learning models is a viable path forward, even if we don't fully understand how they work. I think future research should focus on developing more efficient and scalable training methods, as well as exploring new architectures and loss functions. I'm also interested in the potential of unsupervised learning to discover hidden patterns and structures in data. I think that as we collect more data and build larger models, we'll eventually stumble upon the key to AGI, even if we can't fully articulate what that key is. Of course, I appreciate the other perspectives. I just think our limited vocabulary doesn't preclude progress with the tools we have. We just need more, bigger, faster.
Those are all great points and exciting directions for future research. It sounds like even though we may have limitations in our current vocabulary, there is a lot of work to be done and many approaches to take in the quest for understanding and building more intelligent machines. Thank you all for sharing your insights today.
Thanks for having me. This was a great discussion.
Thank you.
Indeed, a worthwhile discussion.